Good afternoon, ladies and gentlemen. Welcome to Techgig webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is Shorten your testing cycles and get better results with virtualization testing. Our guest speaker today is Shweta Shivaram, Development Lead, IBM Rational, Functional Tester, IBM. Shweta Shivaram has been with IBM Rational for 5 years now, and her interests lie in the latest concepts in quality management space. As part of the development team, she has worked on globalization testing, translation testing, and virtualization testing, in addition to user experience and UI design. In her previous roles, she has worked in multicultural environments and has first-hand experience related to culturally sensitive software. So without further delay, I introduce you all to our guest speaker. Over to you, Shweta. Shweta, you are not audible.
Can you hear me now?
Yes, I can hear you now. If you could start from the first slide, Shweta.
Sure, I'll do that. Sorry about the glitch there. So let me start off. I'm Shweta Shivaram, like Sri Lagna explained earlier, and I'm going to speak to you today about how to accelerate your development and test life cycles using the concept of service virtualization. We'll start off first by defining the challenges that are being faced by teams currently in terms of development and quality management or testing. Then we'll talk about the concept of service virtualization or application virtualization and see how that fits into this picture. Then we will talk about the different systems or applications that you could possibly virtualize, and then we'll do a brief demo of a near real-world scenario system and see how to go about service virtualization on that system. So to quickly start off, let's just list down what are the different challenges that exist in today's software development lifecycle world and see what are those opportunities being presented because of those challenges. So one of the biggest challenges today is definitely quality because of complex test environments, inadequate testing on those environments. You see that defects are caught later in the cycle. They escape early testing, and there is a lot of inconsistency in the data that is used to test between pre-production environments and production environments. And of course, cost of labor is ever increasing. We being in the developing markets and the growth markets, inflation is a big worry, and because of which quality wages for quality management employees has been on the rise, which means that organizations that are looking to growth markets for quality management have to face that direct impact of the inflation and escalated labor costs. Associated with cost is also the fact that the later a defect is found in the application development lifecycle or software development lifecycle, the costlier it is to fix that defect, the costlier it is to maintain your project budgets and keep things in order. Another important aspect that a lot of projects do not realize many a time is the poor asset utilization. You hire quality management professionals, quality management executives, expecting that they would use their skills to the utmost advantage, but we'll see how a lot of these skills are not really tapped into and how we actually spend a lot of the quality management professionals' time in activities other than just quality management. And of course, time to market is crucial these days. We live in the mobile world. We need applications to work immediately. Things that don't work today, we want to fix in the next 5 minutes. And given all this, service virtualization, we'll see how this helps. Currently, we have projects and teams that struggle to cope with this constant delivery, continuous integration. Let's see how service virtualization helps here. So given all these challenges, the opportunities, of course, that exist are to start testing earlier, drive testing cycles from the beginning as soon as possible, as soon as development can start. Try to catch these defects early where they do not weigh down on the project's budget as much as they would if they were found later. Improve the asset utilization in both in terms of human resources as well as in terms of physical or infrastructure resources. Increase the flexibility and the availability of these resources. See how multiple teams can use assets simultaneously without being dependent on each other. And of course, as a result of all of this, see how we can bring down the time to market, increase the levels of testing, increase availability of resources, and thereby maintain the revenue streams of our products. So let's see what then is driving the need for change, right? Like we already mentioned, the increasing cost of quality would mean a direct impact on the project budget because of the increase in wages. And for example, if you look at the graph out here, this year, even with all these economic problems around, the forecasted increase in wages for Indian IT workforce, especially in the quality management workspace, has been about 9.6%, which means that any organizations having to deal with quality management professionals and executives would have to, weigh these things into their project budgets. We already spoke about complexity increasing, how today's applications are no longer just single interface or simple applications that just talk to one backend system or a couple of backend systems. Today's applications talk to a whole wide variety of backend systems. These could be heterogeneous environments. They could be on the cloud. They could be different sorts of backend systems. They could be databases, mainframes. You have ESBs. You have content on the internet. You might be using messaging services from a third-party vendor. You might be using a routing service from a specific vendor and so on. So typically, in order to build a testing environment that can mimic this real-world system that is so complexly integrated, a survey has shown that for a Fortune 500 company to build a quality management lab that can mimic this environment, you would require a little more than probably $250,000, right? So it could be anywhere between $5 to $30 million is what the survey has shown in 2012. And of course, balancing the quality and speed is what is crucial at this point. We see that testers, quality management professionals spend between 30 to 50% of their time on just setting up environments, just configurations, installations, requests for gaining access to systems. So between 30 to 50% of their time goes on all these activities that could have better been used to employ their skills, and their skills are in the space of quality management. So given these challenges, let's see what are the costly points that are, what's costing us today, right? What is costing us? So given all this, we say we are waiting for the system to be ready in order to start testing on it. So that costs us lack of early testing, right? Early in the product life cycle, we don't do significant amount of testing, because of which later in the cycle we are short on time, because of which we then cannot do component or very limited component and service layer testing. There's hardly any test automation in the integration phase. We'll see what happens now in a typical development environment where there are multiple developers contributing towards a particular project. What happens when their code starts getting integrated? We spoke about the complex architecture because of which we cannot really test every single endpoint of our systems today, causing inefficient quality assurance at that point. As a result of all of this, you see an increase in the number of bugs that are found later in the production cycle, right? So when you have your user acceptance tests or your operability tests being performed, then we see a lot of bugs coming out at that point. And like we said, that proves costly. We have to get back to our design sometimes in order to fix these bugs, and that's too late in the cycle, thereby hurting our time to market and causing longer release cycles. So as you see in this diagram here, we're saying that most of the defects today are found later in the cycle, and let's see why this is happening, right? Now in the old world, what happened was we gathered requirements and then developers would start writing their unit tests after they started writing code. And then when multiple developers would bring in their code and start integrating it, what we used to see is what's called the Big Bang, right? So what do we mean by the Big Bang? It's basically a time when multiple defects get introduced at once. There are more unknowns because of which there's greater risk at that point, and the time taken to fix all these unknowns becomes a lot more than anticipated originally, and thereby proves more expensive in terms of project budgets. Once this integration, this Big Bang was resolved, then we had a system integration team that would then pick up this code and run some system tests against it, after which we would introduce a quality gate and then do some user acceptance testing and the operability tests. And while all this was happening, somewhere when the system integration tests would start, the performance testing would start, which again was a little late because then we'd have to go redo the design if we found any performance issues. So here's where I'd like to introduce the concept of application virtualization, right? So what is application virtualization? Let's try and define what it is. So like we said, we have one system that we are interested in testing, and this is called our application under test or a system under test. And this system interfaces with a whole wide variety of different backend systems. Now these backend systems, like we said, could be on heterogeneous environments, they could be on the cloud, they could be different sorts of systems. Now let's try and identify those backend systems that we are constrained by, right? When we say constrained, it obviously poses a challenge of some sort in order to gain access to those systems. And what are the challenges that typically occur in such systems? One could be the unavailability or the inaccessibility of those systems, right? They just could be unavailable because there's a downtime, right? I have a database, I need to do maintenance on it, so I bring it down, and at that time, if it's down for 2 hours, it means my 2 hours of accessing the database is gone. So the system is unavailable, it's inaccessible. It could also probably mean that I have to time share between different teams in my organization. So I might have multiple projects working on, let's say, a mainframe, and I have a single mainframe to test against. And I have the mainframe from 10 this morning to maybe 2 in the afternoon, and then it goes to another team. And so for the time that I have it, I have to schedule all my testing on that system for that time, and after that, I'm just sitting and waiting for the system to be back, to come back to me again. So inaccessibility. Another reason could be that those systems are still under development. I need a database with some basic structure in it, some basic data populated in it. If I don't have that, I can't test against it. So this is about the availability and the constraint that availability poses. Next could be access fees, right? Costly license fees. I might need a Siebel server. I might need an SAP server to set one up or to rent one out, lease it out for a few weeks or months as much as my project demands. It might be quite costly for me to do that, right? Or I could be testing against a cloud-based system, and the cloud might be, even though it's a pay-as-you-go model, it probably is quite pricey as well. The third type of constraint that could probably exist on these backend systems is that they are practically impossible to virtualize, right? They probably are too difficult. You cannot do any sort of hardware virtualization of these machines. They could be mainframe type of systems. They could be remote third-party services. And the traditional approaches that we have are not sufficient in order to virtualize these systems. So given these constraints, what we try to do is we say, let's try and capture the interactions between the application that I want to test and these backend systems that I am constrained by. And once I'm able to capture the information flow between my system under test and these backend systems, I'll try to create a model of these backend systems. And once I can model it, I create what is called a virtual service out of that. And then I can host these virtual services on different systems. They could be on physical machines, they could be on the cloud, they could be, on each developer or tester's own machine or so on. So what we just described was the process of application virtualization. So what we did is we identified those backend systems that we are challenged by, that we have challenges with. We simulate the behavior of, so we try to capture the interaction between our system under test and those backend systems. Then we try to, based on that information, we try to simulate the behavior of this backend system in a software emulator. And then once we do that, we host that emulation or that service on a virtual environment. And this entire process is what is called application virtualization. Now, while we're doing all this capturing and modeling, our developers and testers can continue to use whatever testing tools it was that they were using for their web performance testing, for their manual testing, for their UI test automation, and so on. And the advantage here is that every developer or tester can easily just deploy this virtual service that was created and host it on his own machine. So he's not constrained by the availability or by someone else using that system while he is testing it out. Okay, so let's quickly just list down what are the different types of constraints that we have on this graph sort of figure out here, and see how we can get past this. So what you see on the right side is the physical test environment, and these could be servers. We said physically it could be a server. In terms of software, it could be a web service running on that server. And I might have maintenance constraints on that. I might have a physical system such as a mainframe where I have a limited access period on it. So I could be either constrained by the physical system itself or by the software that's running on it in terms of messaging queues. I might have volume constraints physically posed by a smart device, and through software, maybe input-output is what the volume constraint is caused by. I could have a back-end database system, and I might have volume constraint on this database system. So when application virtualization comes into the picture here, what happens is we put in an agent that can listen and capture the interactions between the system under test and those backend systems that we are constrained by. So once it can listen and capture, it would primarily look at the request response sort of messages or whatever publish messages that take place between the system under test and the backend system. It can then choose to store that information in a configuration management system, in a source code management system, or it could model certain services out of that information. So when we say we are modeling services, the services that we mention on the backend systems are the web services, the messaging queue or the fixed services, the smart device I/O services, or the database transaction services, right? So we can model these services based on the information that we captured and host these services on virtual environments and then use them for testing. Now, going one step further, what we can then do is we've created virtual services. Now these virtual services can be deployed by each team or by each developer or tester on his or her individual machine or individual testing environment. And then we can choose, as our backend systems get ready or as our backend systems start becoming less constrained, to convert these virtual services to the actual live services, right? So I might have my functional testing team that wants to have certain specific configurations for their virtual services. So they might want to test with certain IP addresses and certain proxies and with certain database configurations, while my system integration test team might want to test with different configurations, right, for their databases, for their other systems. It's possible for all these teams now to simultaneously test with their different configurations using different instances of the same virtual service. They can duplicate the virtual service that was created by the agents that we deployed in between the system under test and the backend system, configure it according to their needs, host it on their individual environments. These could be virtual environments, these could be physical environments, and simultaneously test. So while a developer can start his integration testing at the time of coding, a functional test team can pick up the code that has already been delivered and run tests against that code against virtual backend systems. And while all this is happening, the system testing team can also pick up whatever is currently available in terms of an end-to-end test, run the tests against virtual service backend systems, and look for early signs of breakages in an end-to-end scenario. And since this is already possible now, we can also start doing some amount of performance testing right away in order for us to identify issues with our design that might be causing performance hits, right? So what we've done essentially is that we've removed the big bang where multiple developers were trying to put in their code together without any integration testing. We are introducing integration tests at the time of unit testing, which means developers start doing integration tests, or integration tests are run automatically through nightly builds while unit tests happen. And we're moving back the entire cycle of testing significantly earlier in the cycle, which means then performance and all the other tests can start much earlier than before. So what does this do? It accelerates testing, obviously, because we started testing now much earlier than we were before. That causes a reduction in cost, and it also lowers the risk. So now that we've done all this, how does this enable us, to do more testing, do better testing? So what has application virtualization done? It's basically brought in the concept of early testing in the life cycle of development. It gives us a time to test additional components and service layers because we now have enough time to complete this sort of testing. We have the ability to run end-to-end test scenarios because we now have virtualized backend services, so we can run an entire flow. And because we're doing all this early testing, we can identify and fix bugs earlier in the product life cycle. Which then means obviously that we have shortened release cycles and we can go to market much quicker than we were earlier. So a majority of the bugs are found early in the cycle, which means that we do not leave the major bugs or the most critical design related, performance related bugs to production level code. We said that we're using virtualized services for the backend systems, which then means as these backend systems become more accessible, more available, less constrained, we start replacing our virtual services with the actual backend systems. And then as we go towards our quality gates at user acceptance tests or operability tests, we are in a more comfortable and less risk area in terms of defects. So the key features and benefits of application virtualization are that virtualized services can be used when real services are unavailable, are scarce, when you need your backend systems to be dynamic in nature, you need a lot of configuration changes that probably would take time to do on an actual backend system. It's a good option for those who are looking for scalable testing scenarios, looking for low infrastructure requirements because you do not need very high-end physical systems or high-end infrastructure requirements to run these virtual services. Imagine it this way, creating a virtual service of a mainframe against actually leasing or buying a mainframe system to test against. So that's the amount of reduction in infrastructure that we're looking at. We allow testing of complex scenarios right in the beginning of the test cycle because of the availability of these virtual services now. And because of this agent that we deploy that's actually sitting in between our systems and listening to what's happening, it already captured the information that is required, which means this can then be used to automate our testing, our integration testing, which means greater return on investment, quicker identification of defects. And the business value that is achieved as a result of all of this is based on real-time data. It is based on clients and customers who have employed application virtualization in their production environments, in their development environments. So test cycle time goes down by up to 40%, considering that testers now no longer have to sit and wait or sit and create these back-end systems, spending their time raising requests, spending their time setting up systems, configuring systems, installations, and so on. The defects are reduced by up to 30% because if we find a bug early in the life cycle, it means all associated bugs that arose as a result of that are now reduced. We fix it right when it is, in its nascent stage, thereby bringing down a lot of later bugs that might be costlier to fix later. So in all, it reduces the overall development and testing time, and as a result, reduces costs related to infrastructure and human resources. So talking quickly about the specific solution that addresses application virtualization, we have what is called the IBM Rational Test Virtualization Solution. And this is a bunch of different solutions that are put together in order to give you this enhanced capability of service virtualization. So the first among them is the Rational Integration Tester, and it is a desktop solution that basically sits between your application under test and the back-end system. So this agent that we talked about that listens and captures the information and then models the services based on that information, this is Rational Integration Tester. The test virtualization server is the server solution that basically then lets you host these virtual services and provides access to different teams in order for them to deploy these services on different agents, on different machines, on different virtual environments, thereby giving them the ability to do 24/7 testing. Right? So it also, because it is a server solution, a centralized repository for your application, for your virtual services, it reduces the infrastructure costs that are inherent with traditional testing systems. And the performance test server then enables you to use these virtual services and run performance tests against your application. So let's see how we remove the dependencies with another example here. So let's say I have an application interface, a website, and team A was earlier testing this application interface with real environments, right? They were using real back-end databases, mainframes, legacy systems, enterprise buses, and different other systems. And let's say team B, C, and D that are also testing are waiting for team A to finish their testing in order for them to be able to access these systems. Now what we've done is we've used this real environment to create a virtual environment, and we just create clones of these virtual environments that are then assigned to these different teams, team B, C, and D, and they can continue testing with their with the application with the help of these virtual backend virtual services. So let's look at how then application virtualization gives you the ability to do continuous integration testing, right? So you have a tester working on a workstation with his Rational Integration Tester and testing the system under test. So Rational Integration Tester, like we said, this creates the virtual services. It can run the tests for you on, on a local stubbing system. Now the tester can then get his test assets from, let's say, Rational Team Concert, which is a source control sort of system. It's used to store all your models and your artifacts that are created by RRT. You can then integrate that with RQM, which would be a quality management solution. It would be the place where your test plans and your test cases are all stored, and you have an entire testing architecture defined out there. Simultaneously, while all this is being done, you can use the performance tester in order to run performance tests against your application under solution. And you have your virtual environments that are being deployed on the RTCP, which then uses agents to deploy these virtual environments on. So you see out here how we have this continuous integration testing that is being done. Every time there is a change made to the code or to the application, you have an integration build that is running off. It could be a nightly build, it could be twice a day builds that are constantly incorporating changes from the development team. And while these changes are being incorporated, you have integration tests that are being performed on the builds that come out. So a build is certified as green only when it goes through the integration tests that are run against these virtual backend systems. So this also helps in the agile methodology. It helps you to be on demand. You know what are the issues that are caused with every build that comes out. You can isolate the build which has problems. You can isolate the specific work items or the specific tasks that brought in a regression in your system. And this all of this helps make sure that your time to market are not hit because of defects being found late in the cycle. Now, if we look at the software development life cycle, you have the different phases of the life cycle. And let's look at how application virtualization fits into this, right? So right at the beginning, when you have the requirements being chalked out, what are the backend systems that you need to be able to access in order to develop your product or your application. You can already define there what are the constraints for those systems and which of those systems are ideal candidates for virtualization. So early in the cycle, right at requirements time, you know exactly which are the systems that you target for virtualization. And once this happens, you go ahead and create virtual services for these backend systems so that when developers start testing, they can just use these virtual services to unit test the code that they are writing, right? And with the help of the same virtual services, as the developer delivers his code into a consumable build, the test team start using these early builds against these virtual services to do advanced testing, to perform end-to-end scenarios, to perform performance scenarios, and the entire risk in that earlier existed with finding these issues later in the cycle is now done much earlier. And later in the cycle, when we move on to the user acceptance and the operability testing, we start swapping our virtual services with the actual systems, because we all know that the best testing is always done against real systems. So we finally will move to these real systems. So having introduced the concept of application virtualization, I'm going to move into a quick demo of a near real world system, and I'll quickly talk about the architecture of this system. So the system is basically a worldwide traveler system where you can go in and book tickets, book flights, book hotels, book cars, And this is roughly the architecture of the system. So there are three parts of the system that are presented to this user, a flight booking system and a hotel booking system and a flight administration system. And they are all presented through a through the web browser, right? The interface is generated by an Apache Tomcat web server. And the web server then connects to the relevant parts of the system as is required depending on the operations that the user performs. So in this whole system that we have here, we are talking about a Tomcat server being installed, we're talking about a WebSphere application server, we're talking about a WebSphere messaging queue, an MQ queue manager, we're talking about a DB2 backend system, which is our database. And you see that this probably is still a very simplistic example given the current world scenarios, but this is what we're going to try to virtualize and probably a small part of it today. So we'll first take a quick look at how the Rational Test Virtualization Server and RIT, Rational Integration Tester, virtualize web services. So in the original system under test, you have your Tomcat provided application client talking to a backend system, which is your web services, right? So once we do what we do is we put in a proxy between the client and the backend web service, and this is what we call an HTTP proxy. So the proxy basically looks at events that were sent between the system under test and the client, and it routes these messages to Rational Integration Tester or RIT. So RIT now has a repository of the information that was exchanged, and to test if what it had captured was correct, at playback time what it does is it does the same thing that the application client had done originally. It then can connect to a metrics database and write the results onto it. Now there are two types of stubbing that is possible. So we're talking about stubbing here because we want to eventually get rid of the backend systems. That was our ultimate aim. So we can stub locally using RIT itself, which means that RIT would now provide the capability that your backend system earlier provided. So now when you send a request from your web browser, the HTTP proxy is sitting in between your browser and the backend system. It looks at the message. It says, okay, now I have RIT that can service these requests instead of going to an actual backend system. It routes those messages to RIT. RIT knows what is the response that is expected, sends that response back through the proxy back to the application client, and this becomes the local stubbing scenario. Now in hosted stubbing, this is a case where you do not want, so this is a case where you want that this virtual service that you created to be available to multiple teams, multiple different individuals. So this is where we introduce the concept of the test control panel. So RIT has the information, it has the request response message pairs, it knows what is expected. So it creates a stub out of this and it publishes the stub to what is called the control panel. Now once the control panel knows that there is a stub available, it also knows what are the virtualization agents that are running on different systems that are capable of hosting this stub. So once it knows which stubs can be hosted on which agents, it starts the stub on those agents, and then those agents start responding to the requests that are coming in from the client. So this is how hosted stubbing works in the case of web services. Now if you look at the queue manager, what we do is we put in what is called an MQ exit into the MQ queue manager, which then records the information that is traveling between the client and the app server and passes it on to RIT. Now in playback, to identify if what we've captured and what we have finally is right, RIT then poses as the client, sends these messages to the queue manager, which then forwards it to the app server, and then a result is received by RIT and written to the metrics database. Now local stubbing, again here what happens is, in the case of local stubbing, the MQ exit knows that there is the RIT software that is able to answer these requests on the queue manager. So it redirects those messages to RIT. In case RIT is not able to respond to those requests, the exit would then redirect the request to the actual app server. The results are then written to the metrics database by RIT. Now, in the case of hosted stubbing, similar to how it existed for the web services, RIT publishes the MQ stubs to the control panel. Control panel tries to identify which virtualization agents can take care of MQ sort of messages. Once it identifies these agents, it starts the MQ stubs on those agents, and the agents are what now respond to the requests on the queue manager. And again, the control panel can then write results to the metrics database as well. Now, quickly, I'm just going to show you a quick slide on the environments that are currently supported by Rational Integration Tester and the Test Virtualization Server. So there are a bunch of SOA messaging protocols and message formats that you can utilize with the help of RIT and RTDS. So we're going to go in a quick demo right now. I'm going to start off from scratch on a system. So this was the system that we talked about, the Worldwide Traveler. So as you can see here, and I'm hoping the screen has refreshed. Just give me a minute. Yeah, okay. So now that you see my screen here, this is the Worldwide Traveler. The Worldwide Traveler has interfaces to book flights, hotels, and so on. So what I brought up here with a blank screen is my Rational Integration Tester. I'm going to do a quick modeling of the system, right? And let's just see how easy it is to do this. So what I'm going to do is create a service component here. So what we mean by a service component is basically this is a component that offers us the different services that run on my traveling system. So I'm calling it the WW Travel System. And within this, I'm going to create a logical component for every backend system that I'm touching. So we saw we are touching a database, we saw we're touching an MQ system and a WebSphere application server. So I'm going to create quickly logical components for each of these. So what I'm doing here first is creating an MQ connection, right? And on this MQ connection, I'm going to bind this MQ connection with what is called a physical end system. In order to do that, I need to create an environment. Now, this environment would tell me what are the physical systems that I am tying down my logical models to. So I'm going to call this the dev environment. Okay. So I've created an environment here, and as you can see right now there are no bindings on this environment. I still need to create a binding for this MQ system. So for now I'm just going to say okay. I'm going to do a set binding in and create a new MQ manager here. On this system my MQ queue manager is running on with these specific attributes. So I'm just going to put in this information that will help me create the physical model for this system. Once I enter the name of all these MQ related different parameters, I also need to be able to log into this MQ queue manager system. So let me quickly enter the login and password for these systems. And once I have these things in place, I can do what is called a test transport to make sure that I've successfully connected to this queue manager. In the case of MQ, there are specific ways in how we put in the exits. In this case, we're going to use the recording mode of dynamic mirror queues. So that's what I've selected, and I've made sure that I have sufficient queue manager connections in order to get this thing up and running. So what we've just done is basically modeled my backend messaging queue system with just a few clicks. And I'm going to do the same thing here again to create a WebSphere application server logical model. So I'm going to create this application server within the existing components that we created already, which was a WW travel component, right? And Once I select this component, I'm going to create it in the existing environment. I'm going to do nothing else for this moment, just create this component out here. And I'm going to bind this to a physical system. Now the physical system in this case is again running on my local system on a particular port. So I'm just going to put in those details and close this. And the last system that I want to model for this application is a database, because we said we're connecting towards DB2 database. So quickly create a DB logical component. And once I have the logical component, I'm going to create a physical, bind it to a physical component. So I have a DB2 sort of database. So I select the IBM DB2 universal database, put in the name of the database, and put in the authentication details that would be required in order to access this database, right? Once I'm done with this, I can again test the connection here to make sure that I was successfully able to connect to this database. And in just the click of a few buttons, what we have here is a logical system, a logical interpretation of our back-end systems, right? And these are now tied up specifically to the physical systems as well through the bindings. Now, let's do something. Let's say that we know what are the, the things that we want to do with our system now. So, and let's say I've already defined what I want to do with my system in the form of, let's say, some XSD files. I know I want to book a flight. I know I want to make a payment for a flight. So I've already created these XML documents, these schemas. So I'm just going to drag drop these schemas into my schema library. Now that I've drag dropped these schemas into my schema library, I can look at what these schemas have in terms of requests and responses, what the message pattern looks like, and I have a base to start off with. So now that I've done that, let's go to the part that's interesting. Let's see how we can record data against this. I'm going to go back to my logical view, and what I'm going to do is I'm going to start a record on the messaging queue. So I've started a record right now, and I'm going to perform actions on my system that a normal user would do. So let me just fill out some details for the passenger here who wants to book a flight from Stansted to Barcelona, for instance. Put in details, select a card type that is multinational, put in some details for the card number and so on. And once I fill in this data, I'm going to book this ticket. Now, I've gone back to my Rational Integration Tester interface here, and if you look at the recording perspective, the recording studio perspective in the events view, you will see a bunch of statements that have come about, right? So you look at one of them, it tells you that this was related to the booking, and the last one was related to the response for the booking. Then you can see that we selected the multinational type of card, so there was a request made on that, and then there was a response for that. Now what I'm going to do is, you see that I've booked a ticket here with multinational first. I'm going to just select the different types of cards that I want to book my ticket with, and you see for every new type of card that I choose, there is a bunch of additional statements that have been recorded, right? So let me do one last transaction where I'm going to book a ticket with the worldwide card, okay, and come back to Rational Integration Tester. So we now have 4 transactions that occurred for every booking that I made. So the first 4 for the multinational, the second 4 for the global type of card, and the last 4 for the worldwide type of card. So what I'm going to do right now is select all of these and save these, right? So what we did right now was basically capture operations that took place between our backend systems and our system under test. So I'm going to create operations for each of these. Now I can actually go ahead and rename these operations, because right now they're just named after the messaging queues that they were invoking. So I can also associate here a schema with each of these transactions, right? So we already imported some schemas where we said we know what the formats of the messages should be like. So I know what a flight request should be like. I'm just going to import the schema into this flight request. I'm going to do, so this we did for the request type of statement. You see here a response type of statement. I'm going to apply a schema for the response as well. So I'm going to do the same thing. We have a book flight response schema. So I'm selecting this XSD for this case. And then I'm going to select, let's say, just one of these payment types, right? So we had payments through multinational, we had payments through global, and we had payments through the other type of card. So I'm just going to select one here, rename this, and for the request, I'm going to again use the schema that we imported earlier. Right, so once I'm done with this, with the importing of the schema, let's just go in and look at where we want to create the resources. So we created a service component right in the beginning called WW Travel, and that's where we're going to create the resources under. And we will create all these operations under that. And let's look at what this looks like once this is done. So I'm going to quickly lay out this entire system that we've now created, right? So we had a process multinational, we had a web application, WebSphere application server, we had a make booking component, and we had some global and worldwide based transactions. So you see here with the click of a few buttons how we were able to model this entire system with its backend systems and also capture the interactions that were happening between our system under test and the backend systems. We now know the specific components that are being contacted. We know the integration points between these backend points. And now once we create stubs out of these services, we can then go ahead, stop our backend systems and actually host these services on the control panel where we can then run our tests against. So with this, I just did a quick modeling of the system, wanted to show you how easy it was to model the system and create tests against these as stubs. So I'm pretty much done with what I wanted to show at this point. So if there are any questions
Thank you, Shweta, for the insightful presentation. We can quickly take up a couple of questions. You can see some questions which I've already assigned.
Okay.
In the questions.
So the first question is from Vinay Gule, and he says, will you please brief on what is service virtualization and application virtualization? So they are essentially the same thing, Vinay. What you could be virtualizing could be a service that is running, or it could be an application that is running. So they are essentially the same thing. What we really care about is the protocol or the message format that is being used by your application or by your service. And then we identify the message exchange pattern between the system under test and that backend system, which could be a service, it could be an application, and then we virtualize that service. The next question is from C. Sriram, and he says, how does some tests like changing regression tests due to actual production defects be done? Also, how about high-end security tests like pen test, VAPT, etc. be done using virtual environments? Okay, so Sriram, I think what you're saying is you would like to change your regression tests based on changes in the actual production environment, and that is a very valid question. What happens multiple times is that the systems that we have right in the beginning might not really be the final production systems. Designs might change. But as you saw here, recording the changes against a backend system are very simple. Even though your actual production system has changed, it is just a matter of putting RIT in between the system under test and the actual backend system in order to update your schemas. What we saw now was we could very easily import a schema into this entire project. If your schemas are ready, if your production system schemas are ready, you could just pull them in and synchronize them and run your regression tests against the change schemas. In terms of security tests, you're talking about security tests on the back-end systems, on the actual production environment. So Sriram, this is a substitute for your back-end system. Application virtualization, as it is a substitute for your back-end systems at development time, right? Like I've already said, the best way to test is to test with actual systems. If you are not constrained by those systems, go ahead and start testing against the actual back-end systems from day one. This is to enable the cases where those back-end systems are not available, and security testing, by the virtue of the testing itself, needs to be performed with actual back-end systems. So this is something that you would want to probably cater to once you have the final system in place. Okay, the next question is from Shweta. She says, does cost involved is more for the initial setup for application virtualization? So Shweta, the answer to your question would be very project dependent, right? You need to factor in the costs that your project is currently incurring by acquiring licenses for back-end systems, by letting their quality management executives wait while systems are being set up, systems are unavailable. You have to factor in all those costs depending on your project. What are the types of back-end systems you're looking for? What are the costs associated with that? And once you can do some sort of analysis on the costs that your project is currently bearing, we can do an easy analysis of whether the cost of employing virtualization in your system or not is something that is beneficial to the project, right? So Ajit Singh Rajput asks how to create application virtualization for existing applications. So as we saw right now, Ajit, the system that we have currently is actually an existing system. It is a system that is not under development. It actually is a system that is fully productional. What we did here was we just imported the schemas for the system because we've already defined the components here. We've already defined the interactions between these components. We imported these XSDs or schemas. This can be done similarly for your mainframe systems as well through copybooks, etc. And that's the way we model the system. So what we looked at right now was application virtualization for an existing application. The next question is from Sridhar Duruku, and he says, apart from Rational, what are the other tools which are more productively used for virtualization testing with respect to ROI? So Sridhar, there are tools in the market that do service virtualization. The tool from IBM is what is called Rational Integration Tester and the Test Virtualization Server. There are tools from other competing companies that do the same. I think a quick search would on the internet would give you the answer to that. Saurabh Gupta, who's left currently, has asked, what is a metrics database? Is it a real database? Yes. So the metrics database is just a storage for your results. Once you have run your tests, your regression tests or your performance tests or your integration tests against these virtual services, it is a real database. It could either be a DB2 database, it could be an Oracle database, or any database that is supported by RIT, and all the results are stored in this database, right? Navina Raj has said, we must have an idea about the application architecture. Then how is it tester friendly? Great question. So Navina, this is really a good question. So there are different types of people that we have to involve in terms when we're talking about application virtualization, right? So there are practitioners, there are testing leads, there are quality management architects. So for the whole view of your application, right? What does your application talk to? Does it talk to a database? Does it talk to a mainframe? Is it talking to a service on the cloud? Is it using an enterprise service bus? All these questions are questions that probably your testing lead or your quality architect would have. So the design of the system would have to be done by a lead or an architect who has a big view of what is being tested and the end-to-end scenario or the business value that this application is providing to the customer. You will have to know the endpoints, the interfaces, the protocols, the message formats that are being used. So a holistic view is required to model the application that you are trying to test. That said, you might also even if you are dealing at a component level, you probably know that your system is talking to a database in order to get some information, and this might be for a very specific component. So you can do virtualization even for very small components. As a test practitioner, you might not be aware of all the backend systems, but you might be involved with just one or two of those backend systems, and you can go about virtualizing just those systems that you are interested with. Can we parameterize values is another question that Navina Raj has asked, and the answer to that is yes, you can parameterize values. They're what are called tags in Rational Integration Tester. You can quickly convert hard-coded values into values that can be customized depending on who is using the service and what systems they are being deployed on. For instance, development might require a particular type of database in order to perform their testing, whereas functional testing and system testing teams might require a different setup for the database. These things can be tagged or parameterized and customized according to the needs. This is possible, yes. Gaurav Thakkar says, can you please again explain the difference between Rational Integration Tester and the Rational Virtualization Server and their applicability? Sure. So Rational Integration Tester is the component that listens to the information that flows between your system under test and the backend system. It is the system, Rational Integration Tester is the component that creates the virtual service for you, right? The Rational Test Virtualization Server is the component that provides you the ability to host those virtual services and make them available to different teams. So it provides you the capabilities of a distributed stubbing or a hosted stubbing of your virtual services in order for multiple teams and multiple individuals to access these services and do their testing simultaneously. So the integration tester is just a desktop-based product. It monitors the information flow between the system under test and the backend system, whereas the test virtualization server is the server component of this, and it makes this virtual service available through it. Okay, Manish Chaudhary says, how is RIT different from QTP and MTM? Okay. So RIT is an integration tester. It does not do GUI functional testing. I believe QTP does GUI functional testing. RIT is an integration tester. It does not do UI level functionality tests, right? Ayan says, in case application virtualization has been done onshore, can offshore testers access the virtualized application system through Citrix? And this is a question that I will have to get back. If you can quickly drop me a note on this, I can quickly figure out if this is possible and let you know. Ajay K says, will performance be affected if it is done as part of virtualization? Would it yield better performance? So Ajay, the type of service or the type of backend system you are trying to virtualize, the answer to your question would depend on that. Whether your performance would be better or worse would depend on where you've hosted this service. most likely is that since this virtual service would be hosted on your local machine or on a system that is easily accessible, the performance would probably be better. But of course, that's taking a very simplistic view of this. We'd have to factor in various different complexities that could affect the performance of your system. The next question is by Vinil, and he says, will RIT support Kick's link virtualization? Yes, Vinil, RIT does support Kick's virtualization. Faraz Afshan says, whether usability testing can be done and also performing testing, is it done in RIT? Usability testing is not under the purview of RIT. What RIT does is functional tests, non-GUI functional tests, integration tests, tests of against virtualized services. So the performance testing can be done, yes, through the Rational Performance Test Server, the RPTS. That was another part that we spoke about in the system. So we can do performance testing using virtual services. Usability testing is not something that RIT can do. So I think I'm pretty much done with the questions that were currently there. I hope all of you found this session useful, and I hope this gave you a broad overview of what application virtualization is and how it is beneficial for different projects at different times of the life cycle. Please feel free to get in touch with me in case of any further questions on application virtualization and IBM solutions for application virtualization. Thank you for your time.
Thank you so much, Shweta. This was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of the webinar will be available on techgig.com tomorrow. Till then, thank you all.